Hi, ladies and gentlemen. We're going to take a look at the error associated with polynomial interpolation. We've been saying lots of bad things about polynomial interpolation at high degrees or high orders, and what we want to do now is understand why that is so problematic. So starting here in section 4.3, it's just an introduction back to the Lagrange interpolating polynomials and how we would build an interpolating polynomial as a linear combination of those basis functions, which we described in section 4.1. And then here on page 118 is the form of the error for polynomial interpolation. Remember, polynomial interpolants are unique. It doesn't matter which way we go to end up with our polynomial interpolant. There's only one that goes through a set of points. And the error associated with it is here. And what I want to point out to you, and that's part of the conversation that's following in this paragraph, but it's a really important idea, is the similarity between what this looks like and the Taylor's theorem remainder term. Let's take a look. So here's the remainder term for Taylor polynomials. And the remainder term has this form where we have x minus x naught, where x naught is the point that we have expanded about, raised to the n plus first power, divided by n plus 1 factorial, and then this n plus first derivative evaluated at some xc value, which is in between the point that we expanded about and the point that we are considering. Look at this form over here. It's exactly the same. Don't be thrown off by the xc as a function of x, because xc is a function of x over here as well. We just did not state that explicitly. But xc is always a function of x because it exists between the point that we expanded upon and the value of x that we are considering. And that is certainly the case here as well. So the only difference between this error term and the Taylor polynomial error term is the numerator. And that difference has to do with the fact that the polynomial interpolant is built out of n plus 1 distinct nodes. So instead of having all of the information provided by the derivatives at a single point, like Taylor polynomials, we have the information provided at m plus 1 points, but it's just function information. There is no derivative information involved. So that's the real difference. Everything else, the factorial in the denominator, as well as the n plus first derivative, is looking very much the same. So we want to keep that in mind as we consider what's going on here. First of all, I have defined a function capital Psi. It's PSI. For those of you not familiar, this is capital and this is Psi, the Greek letter Psi, and it is the numerator. So it is this product of x minus the nodes where I've taken all of those and combined them together. And so the error term here, and this just goes through, looks like this. So the numbering's a little bit different. So the subscript on the psi is the x sub n, it's the n value, even though there are actually n plus 1 terms in this product. That's just something to keep in mind. So it's still n plus 1 terms, and then this is n plus 1 factorial, and this is the n plus first derivative. So a lot of the story is contained in these two graphics. Unlike Taylor polynomials, where we are gathering all of our information around a single point, and we know the farther we are away from that point, the worse our approximation for the function becomes. In the case where we have this psi function, which is a product of the different factors going together, we end up with pictures that look like these. And this is the reason why polynomial interpolation using equally spaced nodes, so that's important, everything we've done so far is using equally spaced nodes. It's the reason that it's so bad is because out here at one end of the interval, we have the factors built from the other side which have really large numbers in them by comparison. So let me expand on that a little bit. Here's an example of a psi function for 7 nodes at -3, -2, -1, 0, 1, 2, 3. And where this function is going to perform the worst is when we're out in this range, somewhere between the -3 and the -2, or out here between the 2 and the 3. And the reason is the following. Let's say I'm at -2.5. Then the problem comes from over here. I have a -5.5 multiplied times a -4.5 multiplied by a -3.5. So the terms on the other side of the psi function are large. That's the issue and the reason that I have these significant errors at the end of the interval. Right? The errors out here are large because of the contributions from the other side of the interval. All right, so equally spaced nodes is generally a poor choice when we're doing polynomial interpolation. Now, as I told you in class, low-order polynomial interpolation, where we're using quadratics or cubics, it's okay because there are so few factors in the psi function that it's not too bad. And so we do that regularly. But this example here, right, which contains 20 nodes, has 2, 4, right, almost 4 orders of magnitude of difference in the error between the middle of the interval and the exterior of the interval. There's an example here that shows what we're talking about. And I want to spend just a little bit of time, this is just a little bit of broadening for you, considering Chebyshev nodes. So the way we address this problem is by packing more nodes towards the edges of the interval. Because when we do that, then we are going to necessarily be reducing the contribution from these outer terms in the numerator of the error function. So the best possible nodes are actually these Chebyshev nodes. And let me give you a demonstration as to why that is. So I've pulled up MATLAB here. This top part is just to make some pretty graphics. It's not really relevant. What I've done is I've defined a V vector which contains a series of nodes. Right? So in this case, I have 13 nodes, and I've calculated the length, and I want to demonstrate to you, because this is a valuable tool that you'll be making use of, how we can create our polynomials by taking and building one chunk at a time and just continually multiplying it in. This is similar to what we did with Horner's method, where we build the function recursively iteratively through a for loop. So I've defined psi as a function of x, and I've taken x minus the first entry, so x minus a -6 in this case, and I've divided it by the factorial just to scale it down so I don't have really large numbers. Then we go to the for loop, and starting with the second term in the vector, what I'm going to do is I'm going to build this product. So I'm going to take the current psi function as a function of x, which is this factor right here divided by the factorial, and I'm going to multiply it times the next factor. And then I'm going to come around the loop and do the same thing. So the second time through, my psi has 2 factors in it, and I'm going to multiply by the third one. And I'm just going to keep doing this until I have multiplied in all of the factors through the vector v. And then we'll just take a look at what the plot is coming out of this. So in this case, we have an error plot that looks exactly like what we saw in the textbook. In this case, we have the 13 nodes from -6 to 6 equally spaced, and we see the same type of problem with significant errors at the ends of the interval. So you'll notice it's worth pointing out, right, the worst location, it's not quite halfway between the 6 and the 5. Let me see if I can have the point come up here. So it's around -5.7 or so. We can actually do the exact calculation on that with the derivative and finding the maximum value. But it's important enough just to understand that it's in between the -5 and the -6, or between the 5 and the 6. and it's shaded a little bit towards the outer part of the interval. All right, so let me compare and contrast this with Chebyshev nodes. So here I have some code, which I'll uncomment. VC is my V vector except with Chebyshev nodes. So the Chebyshev nodes are built using this cosine. And the cosine, of course, I'm always going to expand between -1 and 1. And let me just give you the formula for what this is, so you can follow along. So the Chebyshev nodes are found as the cosine of 2k minus 1 over 2n times pi, where k goes from 1 to n, where we have n nodes. And if you think about what this is going to be, the numerator of this fraction is always an odd number. I have a 1, and then I have a 3, and then I have a 5, and I have a 7, and I'm just going to keep this up for however many I happen to have. So then I'm going to divide by 2 times n. So let's do the example we were just talking about, which has 13 nodes in it. So the 13 nodes, then this is going to be a 26, and this is going to continue up to 25. And then it's multiplied by pi. So it's really, I'm making this look like a single fraction, but it's not. They're each individual fractions. So it's pi over 26, and 3 pi over 26, and 5 pi over 26, all the way up to 25 pi over 26, all evaluated at the cosine. And if you think about what this means in a circle, we're going to take these values for the angles like this, and they're equally spaced, but look at where the x values are. Near the end of the interval, we're going to have a lot more x values, and then as we get to the middle, we'll take large jumps, and then the values will be quite tight at the ends of the interval, looking something like that. So that's what we're going to take a look at now. Let me pull the code back up here. And I'm going to do the same thing here. I'm going to create a psi function out of Chebyshev. And so my Chebyshev is built in exactly the same way. I'm building the psi function in the same way. I'm just using different nodes. And then I'm going to plot that error in magenta. And so what we end up with is we end up with a plot that looks like this one here. And let me expand this out because it's quite illustrative. So what you'll notice is we have a lot more points near the end. I think I put them out here, yeah. So this is a comparison. This is a comparison against the equally spaced nodes here versus the Chebyshev nodes. And you can see how the Chebyshev nodes are packed in towards the end of the interval, closer to -6 and 6. And they're spread out more through the middle of the interval. And what that gives us then is it gives us more nodes out here, which shrinks the error near the ends of the interval, and fewer nodes in the middle. And what you notice is the error is equal all the way across the interval. So it's worse in the middle than equally spaced points, but it's better at the end points, and overall it's much better because the error is uniform across the interval. And by uniform, I mean the maximums. Obviously, at the points that we are interpolating, the error is 0. That's why we have these values that come down. So if we have a choice, if we have the opportunity to select points, which sometimes we do and sometimes we don't, whenever we have a choice about selecting points and we're going to do interpolation with polynomials, we want to choose the Chebyshev nodes. All right, so that's the conversation. Let me get this out of our way and take a look back at the textbook. So that's really the conversation and an example, a little deeper example here associated with the Chebyshev nodes, along with an explanation as to exactly what the Chebyshev nodes are. So these values are literally the x values. They are the nodes. There's some discussion here about the error. So this last piece is a really important discussion about error as it's associated between divided differences and what we just discussed. So there's a development in here that shows the error associated with the divided differences, which is given right here. That's the error from divided differences. And then this is the error that we're just talking about, divided differences. And this is the error that is from the theorem. Well, error is the error. We know that the interpolating polynomial is unique, so we can equate those two things. And when we equate the error formula that we talked about in section 4.3 along with the error formula that's derived up here that comes from divided differences, we set those two equal to one another, and what we end up with is yet another look at the important result, one of the important results of divided differences, which is this whole idea that this divided difference with n plus 1 points is equal to the nth derivative of the function evaluated somewhere inside of those nodes divided by n factorial. This is just more information that reiterates this result down here that we talked about when we talked about divided differences. So that's it for polynomial interpolation. Right? The big takeaways are the error is much larger at the ends of the intervals, and the reason is because we have this product of different factors which is stressed at the ends of the intervals, and the way we address that is through Chebyshev nodes. The Chebyshev nodes defined this way give us the best possible error we can have because it levels out the error, the maximum errors across the entire interval. Thanks very much, and I'll see you in class.